Hello everyone, thank you for watching my video. I am Kochakon Kochiri. I am glad to present my work about development of sustainable integrated biorefinery networks in pulp and paper industries. Hope you get some ideas from this presentation. At the beginning of biorefinery, crops such as corn and cassava have been used as biorefinery feedstock. But crop is a food. If we still use crops for biofuel production, it could lead to food competition problems. So non-food biomass become the second generation of biorefinery, where focus on lignocellulosic biorefinery. Pigment technologies take place to fractionate the biomass into building blocks cellulose, hemicellulose, and lignin, and they can produce a wide range of products like petrochemical process. The pulp and paper industry today is the world's largest woody biomass utilization system. It is a large user and producer of biomaterials and bioenergy. Lignin and hemicellulose, which spent chemicals called back liquor, will go to chemical recovery unit. Here, chemicals for pulping process are regenerated and go back to reuse in pulping process. Organic compounds like lignin and hemicellulose are burnt to generate heat for process steam and power generation. Petroleum is also used as fuel in process. The pulp and paper production requires large consumption of chemicals, energy, and water, and it is characterized by low efficiency of raw material and energy consumption, low innovation development, and high product price volatility. Moreover, the printing paper consumption has been diminishing because of increased use of digital media in our hands. The traditional pulp and paper industry needs to develop new value-added product streams to improve process efficiency and profitability. While the first generation biorefinery should be moved to the second generation for sustainable future, replacing petrochemical process. So the integrated biorefinery into the existing pulping process could be a potential pathway for long-term sustainable development of not only the pulp and paper industry but also biorefineries by the many benefits. The systematic methodology can be applied to develop the integrated biorefinery network. There are three stages: synthesis, design, and innovation. The first step is to do superstructure optimization to get the optimum network based on generated superstructure. Process data are collected to generate the superstructure that represents or consider processing rules as the network of possible alternatives. Then the optimum process goes to design stage. Base case design and process analysis was performed based on the data that is generated from process simulation. Then the improvement targets are specified. The process will be redesigned in innovation stage to achieve the targets. And finally get the sustainable network. The results of process synthesis was proposed in our previous paper in Computer and Chemical Engineering journal. The superstructure of biorefinery integrated pulping process was generated and optimized with maximized profit as the objective function. From the superstructure optimization results, the optimum integrated biorefinery network is succinic acid and DME production integrated into the soda pulping process that provide the highest profit. In case of integrated biorefinery into carb pulping process, it can also improve the profit comparing to conventional carb process. For our previous work in Journal of Cleaner Production, biorefinery integrated soda pulping network that shows the highest profit in synthesis stage was designed for succinic acid production by pulp fermentation and integrated with DME production by bag liquor gasification. Also, biomass gasification where generalist bioenergy for the whole network was integrated by feeding biomass waste as bagasse pit and imported biomass fuel for supplementary. The further process evaluation illustrated the process hotspot of integrated succinic acid and DME production is shown lower of net carbon dioxide reduction comparing to scenario of only DME production, involving pulp for sale instead of succinic acid production. So, innovation design for carbon dioxide capture and utilization was implemented to reduce more carbon dioxide emission. As shown in the figure, this innovation was designed for flue gas from biomass gasification feed into lactisol process to capture the carbon dioxide and send pure carbon dioxide steam to methanol synthesis. And then DME is more produced by methanol from this carbon dioxide utilization process. From the results, carbon dioxide utilization scenario can enhance potential of carbon dioxide reduction about 40% with only 1.2% of the profit drop due to high operating cost of methanol synthesis. The innovation design provides more biofuel supply but less power supply due to more power used in lactisol and DME synthesis process. To implement biorefinery system into carb pulping process, we call it Biorefinery Integrated Carb Pulping Network or BIT. For this work, feedstocks for the BIT network are assumed to have different composition comparing to the Biorefinery Integrated Soda Pulping Network or BIS from the previous work. Carb process provides higher yield of pulp and more organic compounds in bag liquor, but less biomass fuel as wood bark. The results of performance comparison between different pulping processes will be discussed in the source and discussion section. Process performance are evaluated in terms of economic, energy consumption, and environmental impacts based on the rigorous simulations. Three different scenarios are considered, including scenario 1 is integration of the gasification-based DME production. Scenario 2 is integration of DME and succinic acid production. And Scenario 3 is integration of innovative carbon dioxide capture and utilization. The BIK consists of the existing car pulping process together with three biorefinery combinations of the black liquor gasification coupled with the DME synthesis and the lactose gas cleaner unit. The biomass gasification combined cycle for process, steam and electricity generation, and the sulfuric acid production. Details of the raw material and products from car process as given in the table are obtained from a preliminary mass balance calculation. Then the integrated biorefinery that was simulated by Ashwin Press to obtain the Laplace process information for further process evaluation. After process design process evaluation was performed in three scenarios. The process flow of each scenario is shown in this slide. Scenario 1 considers only the integration of backliquor gasification for the production and the utilization of biomass fuel in biomass gasification for energy generation. The pulp is sold for paper making. Scenario 2 is to integrate the sulfuric acid production from pulp together with the integrated network of the scenario 1. All pulp produced from car pulping process is sent to the sulfuric acid process. And scenario 3 includes the option of carbon dioxide capture and utilization because the energy consumption increases with the integration of sulfuric acid process in the scenario 2. The carbon dioxide emission from the biomass gasification and power plant also increases. This innovative scenario is designed to utilize carbon dioxide to produce more DME. Prior the emission of carbon dioxide containing flue gas from the power plant is captured by lactose process that already exists. The pure carbon dioxide from the lactose gas cleaner unit is utilized for methanol synthesis by the integration of carbon dioxide hydrogenation process. The produced methanol is sent for the more DNA synthesis. The table shows the results of integrated biorefinery scenario 1, 2, and 3, comparing two cases of conventional Tomlinson boiler and backliquor gasification combined cycle or BLGCC. The BIK network in scenario 1, 2, and 3 improved the profit over the conventional Tomlinson scenario by 6, 40, and 39 million US dollars, respectively. The integration of sulfuric acid process in scenario 2 and 3 do highly promote profitability because of high price of sulfuric acids. Moreover, there exists power available in all integrated network scenarios, provide additional income from the sale of electricity, as well as reduction of petroleum dependence. In scenario 3, although the extra 20,000 tons per year of DME production is acquired from carbon dioxide capture and utilization, the profit decreases around 1.1% compared to scenario 2 due to high operating costs. This chart shows economic performance of each scenario Succinic acid production in Scenario 2 and 3 shows the high performance to enhance the network profit, as shown in the green bar, while Scenario 1 that produced only DME could not provide the notable profit enhancement. Scenario 3 has high operating costs of integrated carbon dioxide utilization, leading to profit drop, in spite of more product income. As shown, BLGCC Scenario can also provide a bit enhancement of profit by enhancing energy efficiency that can see the reduction of power costs. Regarding to environmental impacts shown in terms of net pollutants, including carbon dioxide, SOx, NOx, and PM10, the net gas is the difference between the total gas emission and the potential reduction of gas, including the biomass utilization, the diesel replacement by DME, the petroleum-based succinic acid production, and the generation of bio-based electricity. The Scenario 2 and 3 discharge carbon dioxide and pollutants by twice times more than Scenario 1 because succinic acid production demands higher energy and utilizes more biomass in biomass gasification for energy supply. Scenario 3 achieves the highest net carbon dioxide reduction, improving about 20% compared to BLGCC and up to 140% compared to CO2. The total emissions of carbon dioxide in the biorefinery integrated networks are highly larger than the total emission from conventional gases. All scenarios of integrated biorefinery show negative value of net pollutants. They have high potential to reduce the pollutants by implementing biorefinery activities. And scenario 3 gives the lowest value of net pollutants, whereas conventional combustion boilers show positive value for all net pollutants because of fossil fuel consumption. The results of performance comparison between carb process and soda process implementing the same biorefinery system. To meet the steam requirement through the biomass gasification combined cycle unit, the BIK requires more supplementary biomass than BIS because the availability of the leftover biomass residues from carb process is less. The carb process in Scenario 2 and 3 can produce more succinic acid due to higher pulp yield. A reduction of 30% in the net carbon dioxide is observed in Scenario 2 and 4% in Scenario 3, comparing to soda process. The Scenario 3 and Scenario 3S can reduce the net carbon dioxide and other pollutants together with a profit drop. However, Scenario 3S shows higher profit because of higher DME production. In Scenario 3, the higher sulfur content in the syngas is due to sodium sulfide used as carb pulping chemical. This causes a lower flow rate of the pure carbon dioxide stream for methanol synthesis, so the less amount of DME shows in Scenario 3 despite more carbon dioxide emission. For case 1, Scenario 1 gives higher profit compared to zero one is due to the more expensive price of carb pulp. In contrast, test two appear similar. Only 4% higher profit is obtained with zero two, although the amount of succinate acid is more in zero two. The higher demand of energy in the carb pulping process increase the operating costs and reduce power income. More succinate acid production and more biomass gasification operation in zero 3 leads to higher profit and lower net carbon dioxide than zero 3 is, despite lower DME production. For the conclusions, the biorefinery integrated car pulping network shows a great potential for transformation of the conventional car process into a more sustainable, and it shows a better performance than biorefinery integrated soda pulping network due to larger environmentally friendly activities. Thank you for your attention and all support.